Welcome to HPC News Bytes, a weekly show about important news in the world of supercomputing, AI, and other advanced technologies.
Hi, everyone. Welcome to HPC News Bytes. I'm Doug Black of Inside HPC, and with me is Shaheen Khan of OrionX.net. Jensen Huang spoke last night, U.S. time, at the big Computex conference in Taiwan, and with his keynote came the expected raft of NVIDIA announcements. And as we've noted before, NVIDIA's ambitions are an engine that knows no rest. Either they're announcing new technology that pushes the AI compute envelope, or they're forming new business alliances that extend their reach across the AI compute complex. Among the news from Computex is what NVIDIA calls DGX Cloud Lepton, which connects NVIDIA GPUs among various cloud partners. That means a customer can draw on NVIDIA Blackwells that reside on CoreWeave, Lambda, or Crusoe, and other cloud platforms. NVIDIA also announced NVLink Fusion, designed to speed chip-to-chip communications, that they'll sell to other chip designers for building custom AI systems with multiple chips integrated together.
High-end networking gear for NVIDIA chips have been in short supply, so it's not clear whether this is a way to expand production or really an effort to make NVLink more of an industry standard, or maybe both. Computex has emerged as a major global show and an opportunity to catch up with tech trends in Asia in general and Taiwan in particular. So vendors also make a lot of announcements focused on that part of the world. NVIDIA announced big supercomputers to be built in Taiwan, including one at their National Center for High Performance Computing, NCHC, and also talked up HPC quantum integration and the use of GPUs to facilitate quantum computing research and also to emulate quantum systems. Intel had demos of its first chip coming out of their new 18A factory. That'd be Panther Lake, targeting high-performance notebooks and other mobile processing. They also announced new workstation GPUs called Arc Pro for AI and graphics, and their server AI chip, Gaudi 3, that is now also available on a PCIe card. The conference is just starting, so we'll catch up with other announcements next week.
Jack Dongarra is one of the leading lights of our industry, and he was a special guest, by the way, of this podcast in 2022. His recent op-ed in the publication called The Conversation discussed the state of HPC. He called for more attention to traditional HPC, not just AI, and he warned that the nation risks falling behind without a long-term national strategy and federal investment in several areas, including R&D, research at universities and national labs, procurement and deployment of high-end systems, workforce development, new algorithms, and AI HPC integration. He also called for sustained funding models that avoid boom and bust cycles tied to one-off milestones or geopolitical urgency. And he calls for more public-private collaboration to bridge gaps between academic research, industry innovation, and national security needs. By the way, Shaheen, Jack's article has created something of a stir, including a feature story on Politico.
We've talked about public-private partnership, P3 here, and the important role it plays in advancing society. On the technical side, he mentioned the gap in memory speeds compared to processing speed, the urgent need for more energy-efficient performance, the industry's growing focus on low-precision arithmetic driven by AI, while many HPC algorithms continue to need 64 bits, and then assembling all of the above into exascale systems and beyond. Of course, as you all know, Jack's a pioneer of matrix algebra for computational science, and his work includes the development of the LINPACK library and its associated benchmark that is used to rank the top 500 list of the world's most powerful supercomputers. It turns out computational modeling of much of nature can take advantage of matrix algebra, and that includes AI. In his conversation with us, he mentioned ongoing work to look for ways to leverage low-precision hardware to achieve high-precision results. The relatively recent HPL-MXP mixed precision benchmark is an example of that. But many scientific algorithms require actual 64-bit hardware. AI today seems effective with very low precision arithmetic, but as AI becomes more physics-based to mimic reality, it is possible that it too will need 64 bits in a hurry.
At its recent Foundry conference, Intel made news in the chiplet space, announcing the Chiplet Alliance that includes Intel, Ansys, ARM, Cadence, Siemens, Synopsys, and other companies. The effort dovetails nicely with the UCIe consortium that aims to facilitate connectivity among chiplets. The basic idea with chiplets, which are small modular dies, is to connect and combine them in a package formulated into a new and more complex chip. It's like using a Lego set for chip assembly. The chiplet concept isn't new, but it's caught on in recent years in the advanced computing area because the conventional way of developing high-end chips has become complex and enormously expensive.
We've talked about a time when a chip designer could select the capabilities they want from a menu of chiplets or tiles, add them to, say, a shopping cart, and click a button, and it is all incorporated and produced in a custom chip. That sort of mass customization could be the way to address the needs of large and small markets. You could go another step and include those basic capabilities into your cluster configurator, let's say. So you're not selecting a brand of chip, but multiple brands of chiplets, possibly produced in different technologies according to your specific need, and out comes a customized cluster, and the software layers that make your apps take advantage of what the hardware provides. That sure looks like a worthy stop on the roadmap to technology nirvana. These ideas have been around for a number of years, and a lot of people are working on them. Chiplets were a solution to the ever-growing size of chips. They enable super large chips and also reduce complexity by compartmentalizing things. Chips reside on a motherboard that traditionally had a lot of other chips and other electronics on it. But as chips get larger and larger, they leave less and less for the motherboard. The Apple M1 chip already pointed in that direction in 2020. If the whole system is really just one big chip, you kind of have a mother chip instead of a motherboard, and that really changes system design and packaging. So the key now is to have a large enough menu of IP and chiplets and tiles, and a cross-industry standard helps with that. And then to use it for small and large chips so everyone can participate and the ecosystem is larger. Very interesting and exciting to watch. All right, that's it for this episode. Thank you all for being with us.
HPC News Bytes is a production of Orion X in association with Inside HPC. Shaheen Khan and Doug Black host the show. Every episode is featured on InsideHPC.com and posted on OrionX.net. Thank you for listening.